Welcome to our deep dive into the fascinating world of moving coil galvanometers. These devices play a crucial role in measuring electric current with high precision. Today we'll unravel how they work, why they're so important, and where you might encounter them in real life. Whether you're a student, a hobbyist, or just curious about science, this journey will help you understand the magic behind these sensitive instruments. Let's start by exploring what a galvanometer is and why it's a cornerstone in the field of electrical measurements. Moving coil galvanometer is an instrument used to detect and measure small electric currents. It operates on the principle that a current-carrying coil placed in a magnetic field experiences a torque. This torque causes the coil to rotate, and the amount of rotation is proportional to the current flowing through it. The device is highly sensitive, making it ideal for laboratory experiments and precise measurements. Let's look at the main components that make up this remarkable instrument. Moving coil galvanometer consists of several essential parts: a rectangular coil of wire, a strong permanent magnet, a soft iron core, a suspension system, and a pointer attached to a scale. Each component has a specific role in ensuring the device's accuracy and sensitivity. The coil is free to rotate between the poles of the magnet, while the soft iron core enhances the magnetic field. The suspension system allows smooth movement, and the pointer provides a visual reading. Next, let's break down each part in detail. The heart of the galvanometer is the rectangular coil, typically made of thin copper wire. This coil is wound on a lightweight frame to ensure it can move freely with minimal resistance. When electric current passes through the coil, it interacts with the magnetic field, generating a force that causes the coil to rotate. The number of turns in the area of the coil directly affect the sensitivity of the instrument. A well-designed coil is essential for accurate current detection. Permanent magnet in a moving coil galvanometer provides a strong and uniform magnetic field. This field is crucial because it interacts with the current-carrying coil to produce the torque needed for measurement. The magnet is usually shaped to maximize the field strength in the region where the coil moves. High-quality magnets ensure that the galvanometer remains sensitive and reliable over time, making them a vital component of the device. Placed inside the coil, the soft iron core serves to intensify the magnetic field. Its high permeability allows magnetic lines of force to concentrate, making the device more responsive to small currents. The core is carefully shaped and positioned to ensure the field remains radial, which helps the coil move smoothly and linearly. This design feature is key to the galvanometer's precision and accuracy. Suspension system in a moving coil galvanometer is typically made from a thin conductive wire or ribbon. This system supports the coil while allowing it to rotate freely with minimal friction. The suspension also acts as a conductor, carrying current into and out of the coil. Its delicate construction is crucial for the instrument's sensitivity, as even the slightest resistance can affect the readings. Proper maintenance of the suspension ensures long-term accuracy. Pointer attached to the coil moves over a calibrated scale to indicate the current's magnitude. As the coil rotates in response to the current, the pointer's movement provides a direct visual reading. The scale is usually marked in microamperes or milliamperes depending on the instrument's sensitivity. Clear markings and a lightweight pointer are essential for precise measurements, making this component user-friendly and effective. Moving coil galvanometer operates on the principle that a current-carrying conductor placed in a magnetic field experiences a force. In this device, the coil acts as the conductor. When current flows through the coil, it interacts with the magnetic field, producing a torque that causes the coil to rotate. The angle of rotation is proportional to the current, allowing for precise measurement. This fundamental principle underpins the galvanometer's effectiveness. When the coil in a moving coil galvanometer carries current, it experiences a torque due to the interaction with the magnetic field. This torque causes the coil to rotate, and the attached pointer moves over the scale. The amount of deflection is directly proportional to the current passing through the coil. This linear relationship is what makes the galvanometer such a valuable tool for measuring small currents accurately. To ensure the coil returns to its original position after the current stops, a restoring torque is provided by the suspension system. This torque acts in the opposite direction to the deflecting torque. The balance between these two torques determines the final position of the pointer. This mechanism ensures that the galvanometer provides stable and repeatable readings, which is essential for reliable measurements. Damping mechanism is often included in moving coil galvanometers to prevent the pointer from oscillating excessively. This is usually achieved by attaching a thin metal strip or using an air vane. Damping ensures that the pointer quickly settles at its final position, allowing for faster and more accurate readings. Without proper damping, the instrument could give unreliable results due to prolonged oscillations. Sensitivity of a moving coil galvanometer refers to its ability to detect small currents. Factors affecting sensitivity include the number of turns in the coil, the strength of the magnetic field, and the quality of the suspension system. High sensitivity is desirable for laboratory experiments where precise measurements are required. However, too much sensitivity can make the device prone to external disturbances, so a balance is necessary. Moving coil galvanometers are designed to measure very small currents, typically in the microampere or milliampere range. The range can be adjusted by changing the resistance in series with the coil. For larger currents, a shunt resistor is used to bypass excess current, protecting the delicate coil from damage. This adaptability makes the galvanometer suitable for a wide variety of applications. Zero adjustment is an important feature in moving coil galvanometers. It allows the user to set the pointer to zero before taking measurements, ensuring accuracy. This is usually achieved by adjusting a screw or knob that changes the tension in the suspension system. Regular zero adjustment is necessary to compensate for mechanical drift and maintain reliable readings over time. Moving coil galvanometers are widely used in physics and electronics laboratories. They are essential for experiments involving the measurement of small currents, such as studying the properties of materials or verifying circuit laws. Their high sensitivity and accuracy make them a preferred choice for educational and research purposes. Let's explore some specific experiments where galvanometers are indispensable. One classic application of the moving coil galvanometer is in the Wheatstone Bridge circuit. Here, the galvanometer detects the balance point by indicating zero current flow. This allows for precise measurement of unknown resistances. The device's sensitivity ensures that even the smallest imbalance is detected, making it a key component in this widely used experimental setup. Moving coil galvanometers are also used in potentiometer circuits to detect null points. When the potential difference across the galvanometer is zero, the pointer remains at rest, indicating a balanced condition. This property is exploited to measure unknown voltages and compare electromotive forces with high precision. The galvanometer's accuracy is crucial in these measurements. Moving coil galvanometer can be converted into an ammeter by connecting a low resistance, known as a shunt, in parallel with the coil. This allows the device to measure larger currents without damaging the sensitive coil. The scale is recalibrated to reflect the new measurement range, making the galvanometer a versatile instrument in electrical testing and troubleshooting. Similarly, a moving coil galvanometer can be transformed into a voltmeter by connecting a high resistance in series with the coil. This setup allows the device to measure voltage across components in a circuit. The scale is adjusted to indicate voltage values, expanding the galvanometer's usefulness in both educational and practical applications. Moving coil galvanometers offer several advantages, including high sensitivity, linear scale, and low power consumption. Their ability to provide accurate and repeatable measurements makes them ideal for scientific research and industrial testing. Additionally, their robust construction ensures long-term reliability, even with frequent use. Let's look at some of the reasons why these devices remain popular in modern laboratories. Despite their many strengths, moving coil galvanometers have some limitations. They are generally suitable only for direct current DC measurements and cannot be used with alternating current AC without modifications. The delicate coil and suspension system can be damaged by excessive current or mechanical shock. Understanding these limitations helps users operate the device safely and effectively. Proper care and maintenance are essential for the longevity of a moving coil galvanometer. Regular cleaning, careful handling, and periodic calibration help ensure accurate readings. Avoid exposing the instrument to strong magnetic fields or mechanical shocks, as these can affect its performance. By following these guidelines, users can keep their galvanometers in top working condition for years. Moving coil galvanometer has a rich history dating back to the 19th century. Early versions were developed to detect and measure electric currents, playing a pivotal role in the advancement of electrical science. Over time, improvements in materials and design have made the device more sensitive and reliable. Understanding its historical context helps appreciate its significance in modern technology. Development of the moving coil galvanometer is credited to several inventors, including Johann Schweger and André-Marie Ampère. Their pioneering work laid the foundation for modern electrical measurement instruments. Their contributions continue to influence the design and application of galvanometers in laboratories and industries worldwide. Today's moving coil galvanometers benefit from advances in materials and manufacturing techniques. Modern devices use lightweight alloys, precision bearings, and improved magnets to enhance sensitivity and durability. Digital readouts and automated calibration are also becoming common, making these instruments even more user-friendly and accurate. Moving coil and moving iron galvanometers are both used to measure electric current, but they operate on different principles. Moving coil types are more sensitive and accurate, making them suitable for laboratory use. Moving iron galvanometers, on the other hand, can measure both AC and DC but are less precise. Understanding these differences helps in selecting the right instrument for specific application. Moving coil galvanometers are indispensable tools in electrical engineering. They are used for testing, troubleshooting, and calibrating circuits. Their precision allows engineers to detect even the smallest currents, ensuring the reliability and safety of electrical systems. The device's versatility makes it a staple in both educational and professional settings. In classrooms and laboratories, moving coil galvanometers are used to teach fundamental concepts in electricity and magnetism. Students learn about current, voltage, resistance, and the interaction between magnetic fields and electric currents. Hands-on experiments with galvanometers help reinforce theoretical knowledge and develop practical skills. In using a moving coil galvanometer, it's important to follow safety precautions. Always ensure the current does not exceed the instrument's rated capacity to avoid damaging the coil. Handle the device gently to prevent mechanical shocks. Proper safety practices not only protect the instrument but also ensure accurate and reliable measurements. If a moving coil galvanometer gives erratic or inaccurate readings, several factors could be at play. Check for loose connections, damaged suspension, or magnetic interference. Regular inspection and maintenance can help identify and resolve these issues quickly, ensuring the device remains reliable for all your measurement needs. Calibration is essential for maintaining the accuracy of a moving coil galvanometer. This process involves comparing the instrument's readings with a known standard and making necessary adjustments. Regular calibration ensures that the device provides reliable and consistent measurements, which is especially important in research and industrial applications. Environmental factors such as temperature, humidity, and external magnetic fields can affect the performance of a moving coil galvanometer. It's important to use the device in a controlled environment and avoid placing it near strong magnets or electrical equipment. Taking these precautions helps maintain the instrument's accuracy and longevity. Modern moving coil galvanometers are available in portable designs, making them convenient for fieldwork and on-site measurements. These compact instruments retain the sensitivity and accuracy of their larger counterparts, allowing engineers and technicians to perform precise measurements outside the laboratory. Some modern galvanometers feature digital integration, allowing readings to be displayed on electronic screens or transmitted to computers for analysis. This advancement enhances data accuracy, storage, and sharing, making the instrument even more versatile for research and industrial applications. Moving coil galvanometers are vital in scientific research, especially in experiments requiring precise current measurements. Their high sensitivity and reliability make them indispensable for studies in physics, chemistry, and engineering. Researchers rely on these instruments to gather accurate data and validate theoretical models. In industry, moving coil galvanometers are used for quality control, equipment calibration, and monitoring electrical systems. Their precision helps ensure that machines and processes operate within safe and efficient parameters. The device's robustness and accuracy make it a trusted tool in various industrial settings. As technology advances, moving coil galvanometers continue to evolve. Innovations in materials, digital integration, and miniaturization promise even greater sensitivity and versatility. These improvements ensure that the galvanometer will remain a valuable tool for scientists, engineers, and educators well into the future. To recap, the moving coil galvanometer is a sensitive and precise instrument for measuring small electric currents. Its core components, coil, magnet, iron core, suspension, and pointer, work together to provide accurate readings. The device's applications span education, research, and industry, making it an essential tool in the world of electronics. Many people have questions about moving coil galvanometers, such as how to maintain them, what currents they can measure, and how to convert them for different uses. Addressing these common questions helps users get the most out of their instruments and avoid common pitfalls. Understanding the terminology associated with moving coil galvanometers is important for effective use. Key terms include torque, sensitivity, shunt, null point, and calibration. Familiarity with these concepts ensures that users can operate and interpret the device's readings accurately. If you're new to using moving coil galvanometers, start by familiarizing yourself with its parts and basic operation. Practice setting the zero, taking readings, and adjusting the range. With patience and care, you'll quickly gain confidence and make the most of this powerful instrument. Suppose your galvanometer pointer doesn't return to zero. This could be due to a twisted suspension wire or magnetic interference. Carefully inspect the device, straighten the wire if needed, and ensure there are no strong magnets nearby. Regular troubleshooting keeps your instrument in top shape. In a real-world scenario, a moving coil galvanometer might be used to verify the current in a sensitive electronic circuit. Its precise readings help engineers ensure that components are operating within safe limits. This practical application highlights the device's value in both design and maintenance. Moving coil galvanometer remains a cornerstone of electrical measurement. Its unique design, high sensitivity, and versatility make it indispensable in science and engineering. By understanding its principles, components, and applications, you can appreciate the vital role it plays in advancing technology and knowledge.